What is the minimum required ampacity for service conductors for a single family dwelling unit with a calculated load of 150 amps? And the correct answer is 125 amps. Now, I'm going to go through this specific scenario, but this is a much larger topic, and we're just going to scratch the surface in this video. If you want to learn more about this specific topic and how we get there today, you can head over to electricalcodecoach.com, click on the free version, and go down to lesson 8. And it's about 3/4 of the way through that video. It explains it in a little bit more detail. But what we're talking about here is, let's imagine that you are wiring this single family dwelling unit. And you're almost to the end of the project. You're getting ready to mount your service. You go get your meter disconnect combo, you throw it up there, you pipe your rigid through the eave in this case, and you're getting ready to run your 2 hots and a neutral for your service. But the question is how do we decide what size those conductors are? Well, how we do it is we are first going to do a load calculation for the structure and find out what size the service is. In this case, we did a load calc and it happened to land on exactly 150 amps to the amp. Once we get that first number of that initial load calculation, we're going to go to a very special table called 240.6a. And that's where we choose our standard breaker sizes. That's where we learn that there's a 15 amp breaker and a 20 amp breaker and a 30 and so on and so forth. So once you get your known load for the structure, you head over to this table, 240.6a, and you're going to choose the next size up standard breaker. In this case, it happens to be 150 is one of the standard sizes. So legally, you could put this house on a 150 amp breaker. If you choose to do that, now that is now the service size. So when you choose the size of the main breaker, that now is the service size. If you put it on 150, it's now a 150 amp service. If you decide to put it on a 200 in this case and give them some room to grow on, it would then be a 200 amp service. And the reason this service business is so important is because when we get ready to size these wires today, we're going to need to know the size of the service, not just the known load. And here's why. So we've chosen a 150 amp service. And for this code, we're going to head to 310.12. 310.12 in the 2020 and later. And in the 2017 and previous, I think it's 310.15B7. B as in Bravo. 310.15B7 if you'd like to follow along. Let's look at the paraphrase code language. Let's look at the code language first, and then we'll deal with that. So for services rated between 1 and 400 amps, the service conductors providing the total load for a single family home, or the service conductors providing the total load for an individual unit of a 2-family or multifamily residence, can have the ampacity of, and this is paraphrase language, that's why it doesn't flow as well as the code. They're allowed to have a ampacity of 83% of the service rating size. If there's no adjustment factors needed, there actually is a cheat sheet table in the NEC that you don't have to do this math. You can just say, hey, I've got this size service, use this size wire, but I don't want to just teach you how to use tables. I want to teach you how to do the raw math and understand what's going on here. What this code is stating is that if you have service conductors and they are feeding the entire dwelling, you're allowed to take that service size and multiply it by 0.83 and take 83% of that service, and then now that new number is actually the amperage that you'll size your wire by. And like I said, we're just scratching the surface today. If you go to the free video in the free version at electricalcodecoach.com, it'll take you to week 8, and it'll explain this in great depth and detail. Because this also, you can use this for feeders on single-family dwellings and the individual feeders for 2-family and multifamily dwelling units, as long as the panel that you're feeding serves the entire structure. It can't be used for sub-panels. All right, now let's get back to ours today. So first we had to do our load calculation. We had to establish the size of our service. Then we had to see if we're allowed to use this code. Is it a single family dwelling? Yes. Is our service in between 1 and 400 amps? Yes. So I am allowed to use the 83% rule. All I have to do from that point is take my service size, and this is where a lot of people get confused. You would not take your load calculation that you actually came up with and multiply it by 0.83. Let's imagine you came up with 140 amps. You still would have put it on 150 amp service because that's the next size up, but you wouldn't go apply the 0.83 to the 140. You must apply that 0.83 to the service itself, the service size. So we take our 150 multiplied by 0.83, and we're going to get 124.5. In my humble opinion, you're going to round up to 125. Then you're going to go to your ampacity table for copper or aluminum, depending on what size your wire, and you're going to find a wire that will cover the new known load, which is 125 amps. And that is how you would correctly size this service riser wire here. According to the NEC, what are the minimum number of 20 amp small appliance branch circuits required for a kitchen in a dwelling unit? And the correct answer is 2. Now let's imagine that we're in this kitchen and we're really curious about how to wire it. How many circuits does it need? Are they allowed to be 15 amp? Can they be tapped off the living room? What's the score here? Well, let's dive into it. We're going to head today to 210.52b1. But before we dive into that code, we're going to pull back and punt. We're actually going to head over to 210.11c1. And that's where we get the initial requirement for these two 20 amp small appliance branch circuits. And the code states that they are required to serve the receptacles that are laid out in 210.52b1, which is where we're back to today. 210.11c1 requires them, and then 210.52b1 starts to show you how to use them. Let's dive into the paraphrase code language. In the pantry, breakfast room, dining room, kitchen, or similar areas of a dwelling unit, the 2 or more 20 amp small appliance branch circuits that were required back in 210.11c1 must serve all wall and floor receptacle outlets that are specified in 210.52a, which is talking about general wall space in these areas, and all countertop outlets specified in 210.52c, and the receptacle outlets for refrigeration equipment. Let's first recap about what we are allowed to do. So first off, we have 2 circuits at a minimum, and they must serve the following locations: pantries, breakfast rooms, dining rooms, kitchens, or similar areas of a home. So you are literally allowed to take these 2 circuits and go, let's say, one of them to the left side of this countertop and one of them to the right. And off the right side, you're literally allowed to hop off, head to the breakfast room, the pantry, and the dining room, and wire all of those receptacles as well. Then let's say if you want to hop off this left-hand side and you want to go wire the refrigerator and then do some of the kitchen wall space, that's okay too. You're allowed to do that with those circuits, and it's absolutely okay. But let's imagine we want to pull a third circuit to this kitchen for the island, we'll say, and we want to use it to service the 2 receptacles that are on the ends of the island in this fake scenario. Well, you're allowed to do that too. But the most important thing that you must remember is that that also is required to be a 20 amp circuit, and it's not allowed to go anywhere except for those specific areas right there. And that's where a lot of people get off the rails in the field. If we go back to 210.11c1, technically C1 through 4. C1 requires those 20 amp circuits for kitchens, and then when you go 2 through 4, it requires the bathrooms to be on a 20 amp circuit, the laundry room, and also the garage. Let's take the laundry room as an example to expound on this point. If you decide, all right, so the code calls for you to pull one 20 amp circuit to your laundry room for the receptacles. That's great. You only have to have one. If you decide to pull another one for the receptacles in the laundry room, it must also be 20 amps, and it must also follow all the requirements that are laid out in 210.11c. The same thing is it's the same thing with the kitchen. If you decide to pull a third circuit for these general areas, that's okay, but it's technically kitchen circuit 3. It must be 20 amps, and it must follow all of the other rules that are laid out for these specific circuits. I used to pull a dedicated dining room circuit, but it's technically not a dining room circuit because it must be 20 amps and it must only serve those areas. It would technically be kitchen circuit 3 or kitchen circuit 4. 5, 6, 7. And for all of those kitchen circuits, we have to be careful when we're back in our load calculation section because each one of those count as 1500 VAs. But that's a lesson for another day. The other thing that I want to watch out for here, so these 20 amp circuits are allowed to serve all of those areas. They're not allowed to serve any other outlets with very few exceptions that are listed in part 2 of this code. But I want to go to one of the exceptions for this specific code. Now, if we go down below 210.52b1, exception number 2, it says, in addition to the required receptacles specified in 210.52, a receptacle outlet to serve a specific appliance is permitted to be supplied from an individual branch circuit. These are defined terms, and it's allowed to be rated 15 amps or greater. What this code is saying is that on top of the 2 required 20 amp branch circuits, you are also allowed to run an individual branch circuit, and you need to look up the definition for that in Article 100. You're allowed to run an individual branch circuit that's rated 15 amps or greater. What this is stating is that on top of your 2 kitchen circuits, if you wanted to run an individual circuit for this specific blender, you are allowed to do that, and it's allowed to be 15 amps or greater, but it shall serve no other outlets. It must be an individual branch circuit. At the same time, you're allowed to pull an individual circuit over for your KitchenAid and make it 15 amps. So if you're an installer or an inspector, just because you see 14 gauge 15 amp wire in a kitchen doesn't necessarily mean that that's a code violation. As long as they've satisfied their 2 small appliance circuits, you're also allowed to run individual branch circuits on top of that as long as you've satisfied those 2. So just to recap today, you're required to have a minimum of 2 20 amp branch circuits in a kitchen. They're allowed to serve pantries, breakfast rooms, dining rooms, and kitchens or similar areas. And you can work that similar area out with your inspector. According to the NEC, what is the minimum distance required between the bottom of an electrical panel and the floor? And the correct answer is the NEC does not specify. Let's imagine that you have this customer and you come to their home and they're wanting to contract you to change out this oddly placed Federal Pacific panel. And when you get in there and start doing a little bit of research, you find out that this used to be a garage. They've built the floor up, which put the panel in an odd place, and they have just lived with it this entire time. Well, they contract you and they want you to put in a brand new panel, but they have one stipulation. They do not want any drywall repair at all. You try to talk them out of it. You let them know it's going to have to be basically back on the floor. But the question is, what are you allowed to do it, and what does the NEC have to say about it? So the answer is yes. In this case, you could put that panel back where it's at as long as you met all the other codes. And the NEC does have a lot to say about that panel placement, overcurrent height, and also working space, 30 inches, 36 inches, 6 feet, all these different measurements from floor to ceiling. But it does not specify how low it can be. But one thing that you have to watch out for with everything that we do and all of your installs in the electrical industry is you have to check the manufacturer specifications. Check them, see if they have a minimum height that you're allowed to install that piece of equipment or that panel board. Maybe from combustible materials, maybe from just the floor itself, it might specify. Also, just like in every other jurisdiction, you have very specific local laws. So make sure to check those. Check out your local laws and see just how low you can install that panel. Of course, ultimately, you have to get the customer's okay to install anything in a manner that might draw strange attention to a room. But in this case, the customer said, we don't care what it looks like. We just don't want to repair the drywall, period. So you come in, you put this panel back where it was, and you are code compliant as long as you met the manufacturer specs and also any local ordinances. Using non-metallic sheath cable, NM, Romex, what is the maximum number of number 12 conductors allowed in a standard 4-inch octagon box without plaster rings that has a depth of 1.5 inches? And the correct answer is 6. And I love the way that this question is worded because it's just like they do in the actual exams. It's full with a ton of useless information. Now, it does have a lot of very useful information, but we don't need to know if it's non-metallic sheath cable. We don't need the point of it saying without plaster rings, because in the absence of that language, we would just assume that there is no plaster ring. And they love to fill your question with lots of useless information to either waste time or to get you to second guess yourself. But let's go ahead and look at what we're talking about today. Of course, we're looking at box fill, and this is the specific box that we're talking about in this question. This is an octagon box. This is an 1.5 inch deep octagon box that you'll use out in the field, usually for lighting outlets. And for this one, we're going to head to 314.16a. It's actually a table, and it's one of my favorite tables because it's easy to read. Those are my favorite ones. On the left-hand side of this table, it talks about our box size. This is where we get all of our dimensions. Today, it's a 4 by 1.5 inches. Then this next column of the table lists our type of boxes. It lists round and octagonal boxes. Then it lists 4 square boxes, 4 and 11/16 boxes, and then device boxes, a bunch of different types of metal boxes that we're used to using out in the field. And across the top, we read that this is our maximum number of wires if they're all of the same size. So if you have all 10s or all 12s, you can actually use this little cheat sheet table right here to make it even easier. You would start on the left-hand side and find your box size, which ours is 4 by 1.5. Then you come to the type of box, which ours falls under the octagonal section. Then we're going to come across until we find 12 gauge wires. Now on this top line is where all the different gauges are listed. And then when you come down here, it tells you the physical number of wires. So we went from box size to box type, then across the top and found 12 gauge. And then we come down and we tee off with that number. And we find today that it's 6 conductors. Great job. I am the electrical code coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. I want to let you know that you can do it. Just keep fighting. Whatever you're working for, whatever level you're trying to push through and get to the next level, you can do it. I'm in your corner. I've got your back. Today I did it a little bit different. On the community tab of our YouTube channel, I showed you 3 different pictures, and I asked you which one was code compliant. If you're not familiar with this, if you go to our YouTube channel at Electrical Code Coach and you click on the community tab, I do a poll, an electrical question, 6 days a week, and usually offer a full video explanation for each one, just like this. So let's go ahead and take a look at the first picture, the second picture, and the third picture. Then we're going to talk about the code and see which one was code compliant. Our first picture here shows our electrical panel and the gas line running underneath. Our second photo shows the gas line running above the panel. And our third one shows the gas line just on the right side of this panel. Which one do you think it is? Let's go ahead and dive into the answer. First, let's take a look at scenario 1, and we're going to look at 2 different paraphrased code sections. The first one is 110.26A3, and the second one is 110.26E, as in echo. The working space must be clear and extend from grade, floor, or platform to a height of 6.5 feet or the height of equipment, whichever is larger. Within this height, other equipment support structures related to the electrical installation, such as concrete pads, above or below the electrical equipment are permitted as long as they don't extend more than 6 inches beyond the front of the electrical equipment. Now there's some new language here. That one there was from the 2020, but this language did stay in the 2023. And it now includes that a part of the installation that's helping be part of the structure, such as a concrete pad that's maybe poking out a little bit, or part of the structure of whatever is holding that panel, is now allowed to be in that workspace as long as it doesn't go out more than 6 inches. 2017 and previous, that language was not there. Now let's look at part E. For this is for indoor installations, and we're not going to talk about any other parts of this code, some special things that you're allowed to do. We're just going to look at the blanket code, and this is for services, switchgear, panel boards, and the like. It says dedicated electrical space, the space equal to the width and depth of the equipment, extending from the floor to a height of 6 feet above the electrical equipment or to the structural ceiling, whichever is lower, must be dedicated to the electrical installation. No piping, duct, leak protection apparatuses, this includes gas pipe or any other pipe, or equipment foreign to the electrical installation are allowed to be in this zone. So the first code says, hey, from the floor to 6.5 feet, that's going to be the working space or the top of the equipment, whichever is greater. The second one kind of takes it up a notch and says for these specific items, you have to have dedicated space for 6 feet above that equipment as well. You can work through some of the ways that you can work around this in the code, but this is pretty general for most cases. So let's go ahead and take a look at scenario 1. We have a gas line running underneath the panel. Well, when we look at our first one, it says, hey, and the second one, it says, hey, the zone below it has to be clear. No other piping or any ducting is allowed to be in the lower zone. And then now let's go ahead and go to our next scenario. Now this one here, we're going to have to use our imagination a little bit. We don't know the depth of this room. Is that 6.5 feet right there? We have no idea. But above this, we need to have it clear all the way to the structural ceiling in this case. And in this case, the gas line is in that zone above the panel. So this one is not going to work either. And finally, our winner for today is the gas line just on this right-hand side. And technically, we would have to look at 110.26a, or let me see where it's at here. It's where it talks about the width. It's 110.26a2, talking about the width of our working space. We have to have our 30 inches or the width of the equipment, whichever is wider. But that's just to one side. And in this case, the gas line's on the right-hand side here, so we are good to go. So you, with all things being equal, just what we're looking at today on this page, you are good to go on this install, and this would be the winner for today. What is the minimum depth of working space in front of electrical equipment rated 1200 amps, 480/277 volt with exposed live parts on both sides of the working space? And the correct answer to this one is 4 feet. And for this one, we're going to head to 110.26a. Now, everything that we're doing in the code is we are first protecting the people and then the property. The people first and then the property. And if done correctly, it's harmonious. And for this one, we're going to head to 110.26. But before we jump into the table of 110.26a, I want to make a clarification here. It's a big misnomer that only electrical equipment that is going to be worked on while energized is required to have the working space. And that's partly true. If it's required, or if it's likely to be worked on while energized, it's required to have the working space dictated in 110.26a. But did you know that all electrical equipment is required to have working space and access? Let's go back to the beginning in 110.26. It says, access and working space shall be provided and maintained about all electrical equipment. And at that point, it doesn't give any dimensions yet. But you have to be able to access all electrical equipment because you might need to work on it. Now, it may be one of those pieces of equipment that truly are going to be de-energized, and it doesn't need to meet the working space in 110.26a like we're getting ready to learn, but it's still required to have working space, electrical working space. Now let's dive in and answer our question for today. And for this one, we're going to head to table 110.26a, and this is going to be one of my favorite tables because it's so simple to read. On the left-hand side is going to be our nominal voltage to ground. Across the top is going to be depending on our condition. And then here, when we tee off with those two items, we're going to find how many feet of working space we're required to have. Let's go ahead and answer our question for today. First, let's start with our nominal voltage to ground. Well, ours was 480/277. But we're only going to be working with that lower number because that is our highest voltage to ground in this case. So we're going to come here and it's going to fall into this middle column. It's if you're in between 151 volts and 600 volts. Then we need to come deal with this condition business. Now down at the bottom is going to list your conditions below this table. Condition 1 is if there's exposed live parts on one side. Condition 2 is if there's exposed live parts on one side and there are grounded parts on the other side, like a block wall or something like that. And then condition 3 is going to be if there are exposed live parts on both sides. So this one, we need to first come to our nominal voltage, which is the middle column. Then we need to slide all the way over to condition 3, and that's where we're going to find this 4-foot requirement. What is the maximum distance allowed between receptacles in a residential dwelling unit's kitchen countertop area? And the correct answer is 4 feet. And for this one, we're going to head to 210.52C1. And this is where we're going to learn all about the requirements for kitchen countertops and in the 2017 and later, kitchen work surfaces. So whether you are dealing with a kitchen countertop by definition or a kitchen work surface, this is how you're going to space your receptacle outlets in those areas. Let's dive into the code. When we get there, we find out that receptacle outlets shall be installed on work surfaces or countertops that are 12 inches or wider. So the first question we're going to ask ourselves, is this countertop 12 inches wide? If it is, or wider, we know that we're going to have at least one receptacle outlet servicing that countertop. Now let's read on. It says receptacle outlets must be installed so that no point along the wall line is greater than 24 inches, more than 24 inches. Let's see what it's saying. You can pick either side of this countertop, starting with the sink here or over here to the right, and we're going to start with our first 2-foot measurement. So from the edge over 2 feet, we have to have our first receptacle within that first 2 feet. Then we're allowed to go up to 4 feet after that, just so that no point measured anywhere is going to be greater than 2 feet if you measure it. Then we need to wrap around this corner, and we also need to finish within 2 foot of this sink right here in this specific scenario. And what the purpose of this is so you can plug in an appliance with a 2-foot cord, and you should be able to plug it in basically anywhere that you set it down. The beauty of this is it keeps homeowners or the general public from using extension cords. And that's what we want to try to avoid at all costs. And really, that's the purpose of all receptacle spacing in the NEC, is to keep us, even me, from using extension cords. I've probably got one around here that I may or may not should be using. But the whole point is we want to avoid that as much as possible. According to the NEC, what is the requirement for the number of receptacle outlets in a bathroom in dwelling units? And the correct answer is D. At least one receptacle outlet must be installed within 3 feet of each basin. And for this one, we're going to head to 210.52D. Now, when we get to 210.52, that's going to lay out the spacing requirements for almost every receptacle that you can imagine in a dwelling unit. And for this one, let's dive to the paraphrase code language. A minimum of one receptacle outlet must be installed in bathrooms within 3 feet of the outer edge of each basin. The outlet should be positioned on a wall or partition that is next to the basin or basin countertop, or on the countertop itself, or on the side or front of the basin cabinet. Now let's stop right there, and then we'll finish reading it here in just a moment. What this is saying is within 3 foot of the edge of that basin. I'm imagining that somewhere on this vanity the basin starts here. And you can just continue, whether you're on the left or right side, anywhere in that 3-foot zone, and you could draw an arch across it. Anywhere in that zone, that receptacle is allowed to be placed. If we have multiple basins, that measurement starts all over again. We are allowed to strategically place one outlet to satisfy the 3 feet for both basins. That's okay. Because here it says 3 feet of the outer edge of each basin. So it doesn't say we have to have one outlet per, but it says that we must have an outlet within 3 feet of each basin. And this is to keep people, again, like we learned yesterday, from running extension cords, especially in bathrooms. Now let's finish reading the code. The outlet must not be placed more than 12 inches below the top of the basin or basin countertop. So we can't be below 12 inches there. And then let's talk about this third part here. It says receptacle outlet assemblies that are approved for countertop use are allowed to be physically installed in the countertop, like a pop-up or something like that. Now you have to be careful with this last part here. There are 2 different major type of listings for these receptacles that are in like the pop-up receptacles. There are some that are listed for work surfaces, and there are some that are listed for countertops. you are going to have the one that is listed for a countertop if you're wanting to install it in like a kitchen island or a kitchen countertop or in the bathroom countertop. It cannot be the one listed for work surfaces. There is a time and a place for that, but it's not around heavy water usage here. According to the NEC, is EMT permitted to be used as an equipment grounding conductor? And of course, what we're talking about here is using the conduit itself as an equipment grounding conductor instead of a wire type equipment grounding conductor. And the correct answer is yes. Now let's break down this scenario. Let's imagine that you have a friend that owns this commercial shop. She gives you a call. She says, hey, I've got one light over my cash register. Could you potentially install me another one? And you're like, sure, I can do it. You drive over there, you pull out a stick of EMT, you pipe it over, you go ahead and get ready to hang the light. In the meantime, you realize that you don't have a roll of green on the truck, and you call me and you say, Coach, can I install this light with no wire type equipment grounding conductor in the conduit? And the correct answer is yes. And we're going to have to go to a couple different code sections for this. And just to make sure that I'm being clear, just so you understand, from this light on the, well, I think it'd be my left-hand side, over to the new light, whatever side it's on as you're looking at it from the screen. As you go from this side to that side, you could potentially just run a hot and a neutral over there and use that equipment, or use the EMT itself as an equipment grounding conductor. Let's go ahead and take a look at it here. EMT, electrical metallic tubing, is permitted to be used as an equipment grounding conductor as specified in 358.60 and in 250.118. Now, when we get over to 358.60, it is the NEC article all about EMT. If you want to learn everything you ever needed to know about installing it, you could go over to EMT. It'll tell you uses permitted, uses not permitted. It'll tell you about securing and supporting. And when you get to .60, it just says flat out EMT can be used as an equipment grounding conductor. And where this code really derives from is back in 250.118, where there is a very long laundry list of items that are allowed to be used as equipment grounding conductors. Let's look at the paraphrase code language here. It says the equipment grounding conductor either accompanied or, my eyes, I just got them worked on, either accompanied or enclosed with the circuit conductors must be one or more of the following types. The first one is a conductor made of copper, aluminum, or copper-clad aluminum. This conductor can be solid, stranded, insulated, covered, or bare, and can take the form of a wire or bus bar of any shape. So that's the one that we're most familiar with. It's called a wire type or a bus type equipment grounding conductor. The one that we're most familiar with is a wire type, the green stranded bare solid wire that you install with your circuits to act as the equipment grounding conductor. That's the one that we're most familiar with. I've only pulled 5 from this list, but it is a very long list of things that you might be surprised you can use as an equipment grounding conductor in lieu of a wire type. The second one is rigid metal conduit. The third one is intermediate metal conduit. And the one that we're talking about today is electrical metallic tubing, EMT. Then it goes on to talk about listed flexible metal and a bunch of other ones, but most of the rest of this list has special parameters that you're allowed to use or that you must abide by if you're wanting to use this as an equipment grounding conductor. So don't just think you're going to pull out some liquid flex and use it without meeting the other requirements that are listed there in 250.118. So you are allowed to use EMT as an equipment grounding conductor itself. Now, oftentimes I'm all about pulling a wire type equipment grounding conductor on top of my EMT. I like to do both just for many reasons, in my opinion. And don't forget that there are specific cases in the NEC where you must pull a wire type equipment grounding conductor. I think there's some rules in HVAC in certain scenarios that you must have a wire type equipment grounding conductor. There are other pieces of equipment in the NEC that require or just the manufacturer specs that require a wire type equipment grounding conductor. I'm not going to get in the business of doing a lot of using rigid metal or EMT as my equipment grounding conductor, although if done safely and properly, there's absolutely nothing wrong with it. I am the electrical code coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. If you ever need anything from me, you can always just email me at electricalcodecoach@gmail.com. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach, and this is the electrical question of the day. What is the maximum height of a main breaker handle above the floor or working platform when it's in its highest position? And the correct answer is 6 feet 7 inches. Now let's just imagine for a second that you've had a customer call you and they want you to come out and give them an estimate on doing a panel change. You give them the estimate, they're excited, they say yes, they've got an old nasty Federal Pacific in this bedroom and they're going to contract you to change it out. Well, when you get there on that day, you see, hey, the main breaker here at this height, no big deal. It's a little bit smaller panel and they've set it a little bit lower. Well, when you get your new panel, nice 40 circuit panel, you find out that it's a whole lot bigger and that main breaker is going to be much higher than the previous main breaker. The question today is how high can that main breaker be located off the floor legally? Well, the correct answer is 6 foot 7, like we learned. So you're like, let's imagine in this situation that it's going to end up being 6 foot 9, this main breaker, because these new panels are so large. And your hole coming in the back is dictating kind of the height of that panel based off of the outside equipment. Happens all the time. So you decide that you're going to flip this panel upside down and put your main breaker on the bottom. Not a problem. As long as the breaker goes from left to right, then you're okay. It cannot ever be installed that if it's an up and down breaker, that it's in the off position while it's up. But if you have a side-to-side breaker, you can likely flip that panel upside down and use it with the main breaker on the bottom. But the question is, am I good to go? Do I have any other considerations for this specific code? And the answer is you do. We are not just in the clear. I put the word main breaker in today's question on purpose because it's a big misnomer in our industry that the main breaker is not allowed to be higher than 6 foot 7. And that's true, not allowed to be higher than 6 foot 7. But did you know that every overcurrent device in that panel is not allowed to be over 6 foot 7? As a matter of fact, there are no overcurrent devices that are allowed to be installed above 6 foot 7 unless they're in one of the conditions that are listed below in the code that we're getting ready to cover. Let's look at the paraphrase code language. It says circuit breakers and switches with fuses must be readily accessible and installed so that the center of the operating handle is no more than 6 foot 7 inches above the floor or working platform, unless one of the following exceptions apply. And there are a few exceptions down below, and usually it has to do with supplementary overcurrent protection. So let's imagine you had a piece of equipment and it also had a localized disconnect right there next to the equipment. As long as the breaker that's feeding that branch circuit is lower than 6 foot 7 and accessible, then it's okay because you can turn it off at a readily accessible location. Then up there, if you want to have another breaker or fuse, that's likely going to be okay. And that's one of the scenarios where you are allowed to do it. But just as a blanket statement, under most circumstances, all of your circuit breakers are going to need to be below 6 foot 7. So just keep that in mind. And in my opinion, like in this scenario today, if you flip that panel upside down and let's say you're not even using those unused spaces and you use all of these lower spaces closer to the main breaker and you're like, oh, none of the breakers I've installed today are over 6 foot 7. If I'm your inspector, I'm going to say that includes also any of the available breaker spaces because we know in the future when someone pulls a circuit in from the top, it is going to they're likely going to use one of the ones closer to the top because it's easier, it's safer to wire. There's not a bunch of wires in their way. So just keep that in mind when you're out in the field. Now that will be subject to your AHJ and how they handle things. I am the electrical code coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. If there's anything you ever need from me, you can always just email me at electricalcodecoach@gmail.com. If you're enjoying these videos and you want to see some specific topics that we talk about or make these questions about, you can just drop it down in the comments below and I will check them out. If you need anything from me, just give me a shout. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach, and this is the electrical question of the day. Which of the following wiring methods is acceptable for fixed wiring in theaters, audience area of motion picture and television studios, and similar locations? And the correct answer is type AC cable containing an insulated grounding conductor. And of course, what we're talking about here is wiring inside of a theater. And the big takeaway that I want us to have from today is if you'll answer these two questions, you'll be able to find where to go and what to do in the NEC. The first question is, what am I wiring? Physically, what am I wiring? Am I wiring a generator? Am I wiring a piece of equipment? Am I wiring a luminaire? And where am I wiring? Is this a wet location, damp location, rated location, explosion proof location? Am I in a theater? If you'll answer those two questions, you will always be able to find out where you need to go in the NEC. Today, we're actually going to be heading to Article 520 for the answer to our question. And in 520, we find in 520.5a, acceptable fixed wiring methods in theaters, audience areas of motion picture and television studios, and similar locations include metal raceways, non-metallic raceways encased in at least 2 inches of concrete, and cables such as MI, MC, and Type AC that contain an insulated equipment grounding conductor. What does the term approved mean in the context of the National Electrical Code? And the correct answer is acceptable to the authority having jurisdiction, the AHJ. And of course, that is your inspector. And for the answer to this one, we're going to head to Article 100, and we're going to look at the definition of approved. And that means acceptable to your inspector. But where do they get the authority to even inspect your job, and what code cycle to go by, and how do they have the authority to approve something? And what are their provisions in the code for approving? Well, let's talk about that a little bit, and then I've got 4 very important points about definitions that you definitely want to stick around for. So first off, in your state, there's likely going to be a state code or a state set of rules that brings all of this together. It might just be a blanket acceptance of a version of the NEC, or there might be a code for your state. And I'm going to use Florida as an example. In Florida, we have the Florida Building Code. They passed a law that the Florida Building Code is law, and then they get together and put all of that together. Inside of there, they will also accept other documents. Sometimes they write some of their own codes. Sometimes they take another document and maybe modify it or accept certain parts of it. And then sometimes they will refer to you further in the study, like in the case of the National Electrical Code. Now, there are some Florida-specific codes that they've added in for electrical, but for the most part, they default to the National Electrical Code, and it lets you know what cycle. That's how we get, first off, what cycle we're on. It's going to go through some type of legislative process in your state, and that's how your inspector knows what to judge you by and what you know to work by. Then someone has to grant your inspector the authority to inspect your jobs. It's not just something they can just be like, oh, well, I'm going to start inspecting jobs now. Somebody has to grant them that. Now, you might be in a county and it's granted a little bit different. You might be in a city and there's a building official, and then there may be chains of laws that give the building official permission to have people under them. Every state's a little bit different. Now that your inspector has a code to judge you by, and he's been granted the authority to be the authority having jurisdiction, he is now, or she is now, your inspector. And they have the ability to approve or disapprove your install. But they can't just do what they want, although sometimes it feels that way when we're out in the field. I was an installer long before I was an inspector, and for every 1 ounce of code knowledge I have, I have 3 ounces of field experience. But with that being said, your inspector can't just make things up. They have to do what's called getting there in the code. We got to go from here to there to there. They have to get there in the code. And it starts in your state most likely at the highest level, and then you work your way down to what code book you're in. This highest level said that we're allowed to use this code book to get there to do this, and then you find it in the book. Then at that point, your inspector is granted a certain amount of authority in interpreting that book, and they have their license on the line. But whether they approve or deny you, they better feel confident of where they found it in the code. In the NEC, there are some provisions for the inspector having the authority to approve something based on their opinion, or that they find suitable. Your state or local government may also grant them the power to look at an install a certain way and say, hey, I think it's okay, I think it's adequate, I think it's safe, I think it's okay. But they better feel confident in it enough if they ever got questioned that they're able to get there somehow. That's why you don't find your inspector just saying, it looks safe, don't worry about it, because they're guarding their license. And just like you are guarding your license, you wouldn't just give somebody a blank check who's never installed electrical to go out and work your name. In the same way, the inspector doesn't want to just sign off on your work just because you're a nice person. It goes both ways. You're protecting your license, they're protecting their license. So just keep that all in mind. Somebody has to set out the code, somebody has to grant them the authority, then they, at their risk of their license, can go out and approve or disapprove something. Now let's talk about the 4 places in the code that I want to talk about when it comes to definition. So the first one is going to be 2020 and previous cycles. We're going to talk about code-wide definitions. Then in 2020 and previous cycles, we're going to talk about the .2 definitions. In 2023 and later, we're going to talk about the removal or moving of .2 definitions. And then I want to talk about the 2023 all definitions in one location. Let's go ahead and dive into that now. So the first one, if you are in a 2020 code and previous, when you go to Article 100, those are code-wide definitions, meaning that every definition that's in Article 100 applies generally to all of the sections of the code and all the articles of the code. When you go to the 2020 and previous code cycles, in individual articles, if there is a definition that only pertains to that article, it's going to be in the .2 section. So 250.2 or 680.2, you'll find a laundry list of definitions that only apply to that article. They only work in that article, and you can't take and use that definition in some other part of the code to make your install work. Or as an inspector, they can't use that definition to deny your install based off of that definition if they're using it incorrectly. And the reason definitions are so important is because they change the rules completely. If it's a laundry room by definition, then all the rules of the laundry room apply. If it is a dwelling unit by definition, then all of the code rules for dwelling units. That's why it's so important that you know and understand definitions, because it can completely change your install, not just on the NEC level, but also in all the other codes and perhaps in your local ordinance or state rules. Now let's talk about the 2023. They got rid of the .2 sections. This is 2023 and later. They got rid of the .2 definitions in each article. They're no longer there. They're using the .2 section for another reason. It might be refurbished equipment. I remember it briefly hearing it, but regardless for today, it is 2023 and later. The .2 definition is the .2 section is no longer for definitions. Now in the 2023, all of the definitions are in Article 100. Every single one of them are there in Article 100. And this is a good thing, ultimately, but it put a whole lot of definitions at the front of the book and a whole lot more time looking things up, but it's just the nature of the beast. The biggest thing that I want us to watch out for here is that now not all of the definitions in Article 100 are code-wide, right? Because they're all there. All the previous .2 definitions are now all moved to Article 100. So this is what they've done. If you see a definition that doesn't have an article in parentheses at the end, and I'm getting ready to show you an example, then it is a code-wide definition. But let's pull up a specific definition here. Not really concerned with what the definition says, but I'm really concerned with this last bit right here. This definition of adapter is only true in Article 520. If you see a definition and then you see parentheses around it, it's only true in that specific article. Keep that in mind. If it doesn't have that parentheses in an article listed, then it is a code-wide definition. And in this case, this definition belongs to code making panel 15, which really doesn't matter to us today. I am the electrical code coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. If there's anything you need from me, you can always email me at electricalcodecoach@gmail.com. If you are liking these videos, if you would hit the thumbs up button on this video, it would help. Also, if you want to subscribe and share with friends. So just remember, 2020 and previous, Article 100 definitions are code wide. 2020 and previous, the .2 sections are in the specific articles. 2023 and later, they've removed the .2 definitions, moved them all to Article 100. And if you don't see an article in parentheses, it applies code wide. If you do, it only applies to that code. Can a feeder be protected by a listed ground fault circuit interrupter installed at a readily accessible location instead of individual GFCIs? Those that are specified in 210.8 and 590.6a. And the correct answer is yes, it is permitted. And we're going to dive into the answer to this here in just a moment, but I thought this would be a great time to recap on the 3 different types of conductors that we use in the NEC. The first one is service conductors, feeder conductors, and branch circuit conductors. Let's go ahead and dive into it now. The first type of conductor that we primarily use in the NEC is a service conductor. Service conductors come from the utility and they go to the first point of disconnect on the structure. Usually from that point out on the load side of the first point of disconnect, they are going to be, that's where our service conductors stop, and we're going to move into the second type of conductor. So let's imagine that we had a meter disconnect combo and we brought our service conductors in to the line side of the main breaker. Then we were going to an indoor panel, and those conductors there are going to be feeder conductors. Feeder conductors are conductors on the load side of the service that come from one panel and go to another panel that has overcurrent devices. So if you feed from one panel and that wire feeds to another panel, and inside of that panel you have more breakers or fuses, those conductors there are feeder conductors. And our final type of conductors are branch circuit conductors. They are the final conductors at the last overcurrent device. So if we went from the service riser down to the top of the meter to the top of that main breaker, those are going to be our service conductors. Then from this meter disconnect combo, we fed to an interior panel. Those are going to be our feeder conductors. And then from there, we go out and wire lights and receptacles. Those are going to be our branch circuit conductors. If you'll just search different types of conductors, electrical code coach, I've got a really detailed study on this, but I thought it would be a great time to recap. Now let's imagine electrical's been real good to you and you've built you a nice house, you got your meter disconnect combo and your service riser. And let's imagine that you want to build you a small little garage just off the house, and for sake of argument, this one we're going to say it's only 5 feet away from this meter disconnect combo. And I'll explain why here in just a little bit. You're going to pipe down, pipe over, pipe up, mount you a panel, you're going to establish your grounding electrode system, and now you're ready to wire this structure. You decide that you want to have 5 20-amp branch circuits, one for each individual set of receptacles, because you're going to be running a bunch of heavy-duty equipment, and you decide you're going to run one circuit for the lighting. You do the math up. By the time you buy the breakers and everything else, you decide it's a little bit cheaper to buy one breaker over here that's GFCI protected and run it over the building. Inspector comes out, says it's totally fine. A couple things that you want to watch out for here is that, yes, this may be code compliant, but if any one of these 5 receptacle circuits or the lighting circuit trip, you're going to be left in the dark and the whole building is going to be without power. Now, you may be really sharp in the code and you say, hey, coach, I don't think the receptacle over or this breaker over here at the house meets the definition of readily accessible. That's okay. I respect your opinion. It would depend for me how far away the garage was, because if you look back at the definition of readily accessible, it does say capable of being reached quickly. If this is like 100 feet away from the house, you could definitely argue that that's not capable of being reached quickly. So just keep that in mind as you install this if you decide to use this provision. And just remember that if one of these circuits trip, it's going to leave the entire circuit in the dark. Which of the following statements is true regarding receptacle installations under sinks? The first option was receptacles can be installed in the face-up position under sinks as long as they are GFCI protected. The second option was receptacles shall not be installed in a face-up position in the area below a sink. Receptacles can be installed in any position under sinks if they are in weatherproof enclosures. And receptacles must be installed horizontally in the area below a sink. And the correct answer is receptacles shall not be installed in the face-up position in the area below a sink. And of course, this is what we're talking about here. And for this one, we're going to head to 406.5 G2, and we are going to take a look at this. And this is what we're talking about. Underneath a sink, if you're doing your garbage disposal or if you're doing your dishwasher, you are no longer allowed to, I think it's 2017 and later, you are no longer allowed to install those receptacles in the face-up position underneath a sink, which makes perfect sense. They've expanded the allowances of installing them face up in countertops and work surfaces as long as they are listed for countertops and work surfaces. But when it comes to under the sink, it's one of the areas where it is prohibited. And I have actually done this in the past, believe it or not. Let's imagine that you're at a house and you are doing, and this would have been on 08 code cycle or the 11, but you're at a customer's house and there's an old nasty crawl space and they want to add a dishwasher or disposal. You just go straight in that underneath that cupboard, drill a hole straight down through the cupboard, through the floor, fish your wire down through there, pop up into a 4-square box, and have that 4-square box be mounted just directly to the floor and plug it right in. Now, kind of an old school way of doing it, but I have done it in the past. Of course, since 17 and later, we've not been allowed to do that, so I've not done anything like that since. But there's lots of ways around this code, and I understand the driver behind this one because, yes, in this case, for one, this GFCI is not in a readily accessible location if it's at the back of the cupboard, in my opinion. But for two, yes, it would trip the GFCI, so it would kill the load side of the GFCI, but you still have hot conductors likely inside of that box, depending on how it was wired. So if you've got water running down in there, yes, you've tripped the GFCI, but you're also creating a bowl for that water to set in, which could potentially leak back up the individual or onto the equipment that it is leaking from. So I understand this code, makes a lot of sense to me. Just wanted to cover it today. I hope you guys are having a great week. If there's anything I can do to help you, you can always just shoot me a text or email me at electricalcodecoach@gmail.com. Let's get to it. When making terminal connections, how should the tightening torque values be determined and achieved? The options were by using a torque wrench set to a standard value, by guessing based off the actual size of the terminal, by using the highest torque value found in the NEC book, or by referring to the torque values indicated on the equipment or instructions. And the correct answer is D. Let's look at the paraphrase code language. It says tightening torque values for terminal connections must be indicated on the equipment or in the manufacturer's installation instructions. An approved means should be used to achieve this indicated torque value. And of course, if you're unfamiliar with what I'm talking about, we're talking about how much do we tighten the electrical connections that we're making up, whether it's in a panel or switches or receptacles. Do we use the 3 squeak method? Do we use the grunt and twist method? Or is there an actual value that we're supposed to be tightening all these connections, and does it really matter? Well, this became a specific code in the 2017 NEC. And it then specifically said, hey, you have to tighten things according to the manufacturer's instructions and specifications. But we could argue that in the 2014 and previous, this code was already into play based off of 110.3b that wants us to install everything according to the listing and labeling instructions. So this has kind of always been code, but 17 and later, it is now a specific code. And we got clarification and more context in the 2020 and 2023. But one thing that I want to get across to us today is that we need to understand the importance of torquing and make sure that we're torquing all of our connections. Now let's talk about a couple of the connections that we need to make sure that we're torquing. Let's imagine that we're installing this electrical panel and it's previous to the 2017 code or the 2017 adoption or later. In a lot of states, a lot of electricians, what we would do is just torque the main connections, all of our big lugs, right? They would all get torqued. That's all the inspectors were requiring. Depending on your jurisdiction, they may have not have been requiring it at all. But did you know that not only are we supposed to be torquing these large connections, but 2017 and later, clearly it states that we have to be torquing even the breakers, the neutral bars, the ground bars, and also all of our switches and receptacles. Anything that has a torque value needs to be torqued, and we need to make sure that we're doing it properly. So where do we find these values at? Let's take a look. You can find them oftentimes on the the panel cover, or the back of the panel box itself. So we're talking about the cover or the box that it's in. Remember, the guts are what the panel are, but we call it often the whole assembly, an electrical panel, but the guts are technically the panel. But on the back of that can that is holding the panel guts, or on the cover itself, or on the door, you'll often find a markup just like this. And you just got to take your time and read it. Here it says A and B, and it clearly says main lugs. If you're using the main lug version, you can use 6 through 300 kc mil wire, and you have to torque it up to 375 inch-pounds. Then when we go here, it says AB if you have a main breaker, which in this case we do. We would go, you're allowed to install 3 gauge up to 300 kc mil, and it has to be 250 inch-pounds. Then it says here for our neutral, it will receive in between 6 gauge and 300 kc mil. We have 375 pounds again. And then our ground, it's talking about the main ground here. You can do a 2-aught to a number 4 wire, and it must be 50 pounds. Then when we get here, we get to neutral and equipment ground bars. Says here in parentheses the small holes. You can do 6 through 4 gauge. They must be 35 pounds. You can do 8 gauge, and it must be 25 pounds, or you're allowed to do 14 through 10, and it must be 20 pounds. And if it's not listed on the can or on the device itself, whether it's breaker or whatever, and often the breakers have it right on there, you will find it in the paperwork that came with the panel box or with the box of switches or the box of receptacles. Sometimes you have to go dig to the manufacturer specifications online, and you'll find that a lot of brands are very similar for the same product, like if it's 2 sets of switches or 2 sets of receptacles. But always make sure that you know your torque spec. Now let's talk about how to achieve this. Well, for all of our larger lugs, we're going to use something like this, which is a torque wrench. This is going to be a wrench style. You're going to have your 3/8 or your 1/2 inch or larger, and you're going to snap on your sockets, your Allen sockets, and you're going to torque it down. But did you know that you can also get torque screwdrivers, and they are your best friend as an electrician nowadays? You get in there, you set it to 12, 15, 20, whatever it is, and boom, 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 boom. You can go through, torque them all down, and make sure that you've got a rock solid connection. I am the electrical code coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's go ahead and get to it. How many receptacle outlets on the countertops or work surfaces are required on the 20 amp small appliance branch circuits in a kitchen? And the correct answer is as many as required by the layout. The NEC mandates that there must be a sufficient number of receptacles to serve the countertop, but it doesn't give a specific number, like an exact number, but it instead gives us a prescription for how to achieve the proper amount. And that number depends on the layout of the kitchen. If you answered 2 today's question, you're likely referring to 210.11c1. Let's take a look at the paraphrase code language. In addition to the branch circuits required by other parts of this section, at least 2 20 amp small appliance branch circuits must be provided for all the receptacle outlets that are specified in 210.52b. So here in this section, it requires there be 2 circuits, but that's not how many outlets there are. Remember, an outlet is the utilization point at where it comes out. And the moment we put a receptacle on it, it all of a sudden then becomes a receptacle outlet where the power comes out at. Now let's take a look at the requirements for the countertops. This is the paraphrase code language. In kitchens, dining rooms, breakfast rooms, pantries, and similar areas of dwelling units, receptacle outlets for countertops and work surfaces that are 12 inches or wider must be installed according to 210.51C1 through C3. These outlets are not to be counted as the receptacles that are required in 210.52A, which are our general receptacles. What this is stating is that every countertop that is 12 inches or wider is going to have at least one receptacle outlet. And then it goes on down through the code to give you the prescription, which we call the 2 foot 4 foot rule. And I have videos explaining that. If you'll head over to electricalcodecoach.com, you can check out our free version of our exam prep. And remember, if you need anything from me, you can just email me at electricalcodecoach@gmail.com. Let's get to it. Which of the following materials is not allowed for grounding electrodes? And the correct answer is aluminum rod. While aluminum is a super versatile material and very integral to the electrical industry, there are a few cases in the NEC where it's actually prohibited, and this is one of them. When we head over to 250.52B2, we're going to find that aluminum is not permitted as a grounding electrode due to its susceptibility to corrosion, which could compromise the grounding integrity. When we head over there, there are a few things that we are not allowed to use as a grounding electrode. B1 is metal piping systems for underground gas. We don't want to use those as part of the grounding electrode system. Aluminum is specifically called out. And then structures and structural integrity of reinforced steel, and the steel that is referenced in 680.26, which of course is our pool equipotential bonding grid. We're not allowed to use any type of the pool structure as part of our grounding electrode system. When securing equipment grounding conductors, grounding electrode conductors, or bonding jumpers, which of the following methods would be a violation? And the correct answer is using a machine type screw fastener that engages one thread. Let's take a look at the feedback. The NEC requires that machine type screw fasteners engage at least two threads or be secured with a nut. A fastener engaging only one thread does not provide adequate security and would be a violation. Let's take a look at the paraphrase code language. In 250.8, the following methods are allowed for connecting equipment grounding conductors, grounding electrode conductors, and bonding jumpers. And this is paraphrase code language. Pressure connectors that are listed, terminal bars, pressure connectors listed for grounding and bonding purposes, exothermic welding, which is CAD welding, machine screws that either engage at least two threads or are secured with a nut, thread forming screws that engage a minimum of two threads within the enclosure, connections that are an integral part of a listed assembly, and any other listed method. Of course, consult the actual NEC for the specific code language. What size copper conductors would you select for a 2 horsepower, 115 volt AC single phase motor terminating to 75° C terminals? And the correct answer is 10 gauge wire. Now for this one, we have several steps. When sizing normal motor conductors, you will use the FLC, which is the full load current, values from table 430.248 for single phase and table 430.250 for three phase. Then you're going to multiply that FLC by 125%. Then we're going to use our primary ampacity table to size our wire based off the column that the question states the terminals are rated for in degrees Celsius. Let's walk through it step by step. First, we're going to head to 430.248 because our question specified single phase. We're going to find our horsepower on the left, which was 2. We're going to come across the top and tee off with our voltage. And then when we drop down, it's going to let us know our FLC. That's going to be our starting value. Then, according to NEC 430.22a, the conductor supplying a single motor must have an ampacity of not less than 125% of the motor's full load current rating. So we take our original 24 amps, we multiply it by 1.25, and that is going to equal 30. Now we need to head to our primary ampacity table. And once we get there, we're going to start on the left-hand side because the question specified copper, and this is the copper side of the table. We'll come down here on the left-hand side, or excuse me, the easier way to do this question, we're actually going to do it in reverse. We're going to start at the 75-degree C column and then come down and find our first wire that will cover our known load, which is 30 amps. And we're going to find that when you get to 12 gauge, it's only good for 25 in the 75 degree. So we're going to need to upsize that to the next size, which is good for exactly 30 amps. And that's going to be our wire that we choose. And then we need to slide over, and we're going to find out that it's actually a 10 gauge wire. What size copper grounding electrode conductor is required for a 200 amp service with 2-watt copper service conductors? And remember, the grounding electrode conductor is the wire that goes from, we'll say, the ground rod to the service enclosures. And the correct answer is a number 4. Now, anytime we're dealing in the exam prep world with a question about grounding electrode conductors, we have a qualifying question. Does it mention the type of electrode? Meaning, does it say when using a ground rod, when using an UFA ground, or whatever? In this case, the answer is no. And in the absence of knowing the electrode, we're going to default to table 250.66 and use it at face value, which we're going to do in just a moment and walk through the process of answering this question. If the question does mention the type of electrode, as an example, a ground rod or an UFA ground, we're going to first go to section 250.66A, B, or C and see if our type of electrode is mentioned in the text. And if it is, that's where we're going to find the answer to our question if it does mention the type of electrode. Now let's go ahead and answer this question. What size copper grounding electrode conductor is required for a service with 2-watt copper service conductors? Does it mention the type of electrode? No. So let's go ahead and head to table 250.66. This is where we're going to size all of our grounding electrode conductors. We always will start on the left-hand side and select from the column of the composition of our service conductors themselves. So on this side, we have 2-watt copper service conductors. So we're going to start here and we're going to go down the copper column until we find 2-watt wire or whatever range that 2-watt wire falls in. Then we're going to cross over to the other side of the table and we're going to look back at our question and ask what type of metal is the grounding electrode conductor itself. And the answer is copper in this case. It wants us to size a copper grounding electrode conductor. So we're going to select from the copper column. And what we would do is follow from this side over. We'd find 2-watt on this side, slide over to the copper column, and we're going to find that it's required to be a number 4. I am the electrical code coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. If you'd like to learn about this very large subject that we break down in a very easy to understand way, you can head over to electricalcodecoach.com, click on the free version, and go to week 10. That's where we cover this topic here. By the end of it, you'll be a pro at sizing all 3 different types of grounding conductors, which include grounding electrode conductors, equipment grounding conductors, and bonding jumpers. Let's get to it. Electrical question of the day. How many amps would a 100-watt light bulb draw on a 120-volt circuit? The correct answer is 0.83. And for this one, we're going to go to our Ohm's law and use pi. Just plug in what we do know. We know that we have 100 watts on top, we have 120 volts, and we're solving for amperage. So all we have to do is divide. We take 100 divided by 120, and that gives us 0.8333. And we're going to select D. Great job. Conductors and overcurrent protection for wind electric systems shall be calculated at no less than blank percent. And the correct answer is 125%. As we see solar and wind expanding, we're also going to see the education needs for them expand as well. Today, what we're talking about is when we're sizing conductors for and selecting overcurrent protection for wind electric systems. How do we do that? Well, let's take a look at the paraphrase code language. When we get to 694.12b in part 1, it lets us know that currents in wind turbine electrical systems shall be treated as continuous. Well, as we've learned in previous parts of the code, that typically means that we're going to multiply them by 125%. Then in part B here, it removes all doubt. It says conductors and overcurrent devices circuits must be sized to handle at least 125% of the maximum current that's calculated in the previous section of 694.12a, and it tells you how to calculate these currents. And then it says that you're also allowed the rating or adjustment of the overcurrent device is allowed to be under these sections of the code, which is 240.4b and 240.4c. And what those sections allow us to do is allow us, when it's 800 amps or less, to protect the wire with a larger overcurrent device as long as we cover the known load. And that's how we get our next size up rule. Let's say we had a known load of 94 amps and we had a wire that was good for 95 amps and we wanted to protect it with a 100 amp breaker. Well, just like in other parts of the code, that would be totally fine. We've covered the known load, which is 94 amps. Our wire is good for 95, and we're allowed to protect it with the next size up, the next standard size, and in this case, we would be code compliant. It's saying that you're allowed to also apply these rules here for wind turbines. What is the total calculated demand for a service where there are two 10 kW ranges in a residential setting? And the correct answer is 11 kW. I don't know if you know this about me, but I love to cook. When me and my wife first got together, that first year, I did a lot of the cooking because I learned how to do it growing up. Over the next few years, while my mother was still alive, she learned how to cook with her, and now she is one of the best chefs that I know. But to answer this question, thankfully, we don't have to do any calculation at all. We get to use one of my favorite tables in the NEC, and that's table 220.55. This is a much more complex subject, and if you want to head over to electricalcodecoach.com, you can learn all about the nuances of the 3 different columns, how to apply them all, and you can learn that absolutely for free if you'll just click on the free version and go to about week 4, you'll find this full lesson. But today, let's answer this individual question. When you're looking at this table, you're going to look first at the left-hand side and find your number of ranges. In this case, we have 2 ranges. So we're going to go down to where it says 2. Then we have to ask the question, which column am I going to be using? Am I going to be using column A, column B, or column C? Well, that is actually decided by the rating of one of the ranges of the individual range if they're all of the same kW, and in this case, they are both 10. So we need to take one of them, which is a 10 kW range, and find out what column we're in. If our range was 3.5 kWs or less, we would use column A. If our range fell in between these values, which is 3.5 to 8.75, we would use column B. And then our range is a 10 kW and it falls in between these values. That lets us know that we need to use column C throughout this entire process. We're going to start on the left-hand side and find our number of ranges, which is 2. Then we're going to cross over to column C and we'll find that the values in column C are not a multiplier, a demand factor. They are in fact a replacement value. So after we do all of this work, we're going to find that the actual demand that you would calculate for a residential service for 2 10 kW ranges is going to be 11 kW. A ground rod or pipe shall be allowed to be installed at up to a blank degree angle if rock is encountered. And the correct answer is a 45-degree angle. Let's take a look at the paraphrase code language. The electrode must be installed so at least 8 foot of its length is in contact with the earth. It should be driven to a minimum depth of 8 feet. However, if rock is encountered, the electrode may be driven at an angle not to exceed 45 degrees from vertical. Alternatively, if rock is encountered at the angle up to 45 degrees, the electrode can be placed in a trench with a minimum depth of 30 inches. The top of the electrode should be at or below ground level unless the exposed end and the connection to the grounding electrode conductor are safeguarded from physical damage as outlined in 250.10. Let's take a visual look at what we're talking about here. Let's imagine we've driven our first ground rod on the left, and then to satisfy other parts of the code, in this scenario, we're going to drive our second ground rod. And let's imagine that we hit rock. We're allowed to install that second or the first or second ground rod up to a 45-degree angle. Now, I don't know if this picture is depicting perfectly 45 degrees, but you can use your imagination. And then in the case that we still hit rock and we're not able to get it that 8 feet, we're allowed to dig a trench 30 inches deep and lay the rod down in that trench. Now, this is where the end part of the code, where it says that the rod should be at or below ground level, you might get two different interpretations from two different inspectors. One of them might say the trench needs to be 30 inches deep all the way across, lay the rod all the way down in it and cover it up. The other one might look at it and say, hey, I want you to still angle it where the top is going to be at or below ground level, but I want you to angle that rod so that connection is still accessible, the acorn clamp connection, maybe even just for inspection. That's up to you and your authority having jurisdiction on how they interpret that code. I would be okay with either one. I think we're going to satisfy the true meaning of this, and that's to have a robust grounding electrode system.
Temporary electric power and lighting installations shall be permitted for a period not to exceed blank days for holiday decorative lighting and similar purposes. And the correct answer is 90 days. And for this one, we're going to head to Article 590. Let's take a look at the paraphrase code language. When we get to Article 590.3, it talks about the time constraints for these temporary installations. Part A is talking about construction. Let's check it out. During the construction period, temporary electric power and lighting installations are allowed during the phases of construction, renovation, maintenance, repair, or demolition of buildings, structures, equipment, or related activities. In Part B, it talks about the 90-day limit. Temporary electric power and lighting installations are permitted for a maximum duration of 90 days for the purposes such as holiday or decorative lighting and similar uses. I am the electrical code coach, and if you'll head over to electricalexamcoach.com, you can check out more questions like these. If you need anything from me, you can email me at electricalcodecoach@gmail.com. Let's get to it.